4 centuries ago, Galileo pointed one of the first telescopes at the night sky, marking the beginning of a new era in our understanding of the universe. Since then, we have come a long way, and Galileo's modest lenses have been replaced by enormous mirrors capable of collecting light from billions of distant galaxies. Well, technological progress never stands still, and right now, we are witnessing the birth of a new generation of astronomical instruments. Yes, you heard that right. This is one of those episodes where we'll talk less about science itself and more about the complex engineering solutions that make astronomy possible. At last, we will take a deep dive into the technology of adaptive optics and find out what this component will offer us in the largest telescope in history. So, welcome. Today, we're talking about the extremely large telescope, the most impressive ground-based astronomical instrument ever built. Size matters. At least in astronomy, this is an undeniable truth that follows from a simple formula stating that a telescope's resolution is proportional to the wavelength of the light it collects and inversely proportional to the diameter of the telescope's mirror. The wavelength parameter is something we cannot change. After all, we don't dictate to celestial objects at which wavelength they should shine the brightest. Therefore, the only way to see smaller and smaller objects is to build larger and larger telescopes. For example, a 2-meter mirror in a reflecting telescope allows us to distinguish objects with an angular resolution of 0.05 arcseconds, almost like spotting a coin from 100 kilometers away. Naturally, larger mirrors provide even greater capabilities, but there is always one problem. Even if we manage to find the perfect location for a telescope, one with the clearest and calmest skies, the atmosphere will still degrade its resolution by at least a factor of 10. There's no escaping this. The very gaseous envelope that sustains life on Earth simultaneously prevents astronomers from seeing the details of the universe. Not only does the atmosphere blur images, but it also absorbs many wavelengths of radiation that are crucial for astronomy. This is precisely why X-ray and ultraviolet astronomy, as well as gamma-ray astronomy, only truly developed with the advent of space observatories. Without them, we wouldn't know about X-ray binary stars, gamma-ray bursts, or even the accretion disks of black holes. Previously unknown processes, inaccessible to ground-based astronomy, became observable thanks to space telescopes. However, it's important to understand that many discoveries are still being made in the visible and near-infrared ranges, where stars emit most of their energy. In recent decades, technology has finally enabled the construction of truly massive mirrors, along with successful methods for counteracting atmospheric turbulence. As a result, ground-based astronomy continues to thrive. It has led to the discovery of the first exoplanets and even the direct imaging of some of them. So, until humanity invents a space elevator or some other fast, cheap, and efficient way to transport large payloads into space, ground-based observatories will maintain a significant advantage. They can be upgraded throughout their operational lifetime, always integrating next-generation instruments. Moreover, the lack of constraints imposed by rocket fairings allows for the design of truly enormous mirrors, providing astonishing resolution. Resolution, in fact, that remains beyond the reach of space telescopes. This is why ground-based astronomy remains an indispensable pillar of science, with extremely large telescopes considered one of its highest priorities. For many years, Europe has played a key role in ground-based astronomy. This is because many of the world's leading observatories are operated by the European International Research Organization, known as the European Southern Observatory. 14 European countries are members of this organization, along with Brazil, whose membership is still awaiting ratification, and Chile, which serves as the host country. ESO has built 3 observing sites in Chile's Atacama Desert, where atmospheric conditions are considered among the best on Earth for astronomical observations. The telescopes of the European Southern Observatory rank among the largest and most technically advanced astronomical instruments in the world. Perhaps the most well-known of these is the Very Large Telescope, VLT, a sort of smaller sibling to the hero of today's discussion. By the way, don't confuse the Extremely Large Telescope, which is still under construction, with the Very Large Telescope. The latter consists of 4 telescopes, each with a mirror diameter of over 8 meters, which are combined into an interferometer. This means they can operate both individually and together, forming an even larger optical telescope. To maintain and reinforce its leadership in astronomy, in 1998, the European Southern Observatory proposed an ambitious, perhaps even slightly insane project: the construction of a truly gigantic optical and infrared telescope with a 100-meter mirror. However, the conceptual design of such a colossal instrument proved too ambitious, presenting significant technical risks. After extensive studies, an international commission recommended reducing the mirror's size to a more modest 40 meters, still an impressive feat. By the early 2000s, the project was given the green light as one of ESO's main strategic priorities. Then, in 2006, during a conference in Marseille attended by over 250 astronomers, the proposed plans were met with great enthusiasm, and ESO decided to proceed with design and construction. Now, in 2025, the extremely large telescope is gradually taking shape. Its home is Cerro Armazones, a mountain in Chile's Atacama Desert, located about 20 kilometers from another observatory on Cerro Paranal, the site of the previously mentioned Very Large Telescope. The site's exceptional astronomical quality is due to its elevation, 3,046 meters above sea level, placing the telescope above a significant portion of the atmosphere that would otherwise distort and scatter light from cosmic objects. Additionally, the local climate is extremely dry, with only about 100 millimeters of annual precipitation and an average humidity of less than 15%, both crucial factors for astronomical observations. While this location provides significant advantages, even a 39-meter telescope cannot reach its full scientific potential without advanced engineering solutions. Around 2028, when the extremely large telescope captures its first light, it will become the largest visible and infrared telescope on the planet, and beyond. Since nothing like it has ever been built before, the engineering challenges are immense. The dome of this colossal structure stands 80 meters tall and 85 meters wide. That's roughly the height of 3 9-story buildings stacked on top of each other. It is an enormous structure with strict positioning requirements to accurately track celestial objects. Essentially, engineers had to devise a way to rotate and move approximately 5,000 tons of steel and glass with millimeter precision. And they had to achieve this in a region of high seismic activity. Yes, the price of a clear sky is an unstable Earth. Chile experiences over 600 earthquakes annually with a magnitude greater than 1.5. To protect the telescope, its structure had to be isolated from the bedrock. Otherwise, if all the energy of an earthquake were transferred to the equipment, especially the mirrors, the consequences would be disastrous. Directly beneath the telescope, seismic isolators have been placed between the foundation layer and the ground. This allows the foundation and telescope to slide horizontally by up to 30 centimeters, absorbing the Earth's movement. Additionally, vertical seismic waves are dampened using hydraulic shock absorbers, somewhat similar to those found in cars, though significantly more complex. The primary structure of the telescope is a complex engineering solution designed to meet 2 critical requirements. On the one hand, it must be rigid enough to ensure that the scientific instruments, and most importantly, the mirrors, remain stable and precisely aligned. On the other hand, the structure must be lightweight enough to prevent the telescope from deforming under its own mass. All of this sophisticated optics and scientific instrumentation is supported by a structure composed of 2 main components: the azimuth structure and the altitude structure. The so-called azimuth structure is responsible for rotating the telescope along its vertical axis, along the azimuth, as the name suggests, or simply put, left and right. To achieve this, the design includes bearing systems mounted on circular rails, which allow for smooth and precise rotation. A distinctive feature of this part of the telescope is the presence of 2 large platforms, each approximately 30 by 15 meters in size. These platforms will host the scientific instruments and auxiliary systems. The generous space is no coincidence. Just like everything else on this telescope, the scientific instruments will be enormous, comparable in size to some space observatories. To give an idea of the scale, one of the 8-meter telescopes from the Very Large Telescope could easily fit on these platforms. At the same time, the mass of the azimuth structure is relatively low, just 1,300 tons, since it is primarily composed of hollow elements. However, it is strong enough to support the second major part of the telescope, which houses all of its advanced optics. This is known as the altitude structure, also referred to as the telescope tube. In the lower part of this 50-meter-long tube, the primary mirror, measuring 39 meters in diameter, will be installed, while the secondary mirror will be suspended high above it on 6 spider-like support beams. The remaining mirrors will be positioned on a 10-meter tower located at the center of the primary mirror's support structure. This entire structure, weighing 1,500 tons, will rotate along a horizontal axis, moving up and down on massive hydrostatic bearings. Large semicircular plates mounted on both sides of the telescope tube will glide over these supports, allowing the structure to adjust its altitude. Thanks to this design, the 39-meter mirror will be able to precisely rotate and lock onto celestial objects with the necessary accuracy. Giant mirrors are essential for transforming tiny, blurry patches into sharp images of celestial bodies. But that's not the whole story. In astronomical slang, telescopes are often called light buckets. The larger the bucket, the more rain it can collect. Some astronomical objects are so faint that only a handful of their photons reach Earth. A larger mirror can capture more of these photons, revealing previously invisible, dim objects in images. However, large monolithic mirrors present a significant engineering challenge. Once they reach a certain size, they become extremely difficult to cast, polish, and, most importantly, securely mount on a telescope. The issue arises because the surface area of a telescope mirror is proportional to the square of its radius. In other words, the difference between a 5-meter mirror and a 10-meter mirror is far greater than it might initially seem. A 10-meter mirror has 4 times the surface area of a 5-meter one, making it at least 4 times more massive. The larger the mirror, the harder it is to design a structure capable of supporting its immense weight, and the mirror itself is prone to deformation under its own gravitational force. The solution is segmented mirrors. By combining multiple smaller mirrors, typically hexagonal in shape, you can achieve the required light collecting area without the need to cast a single monolithic mirror. However, this approach introduces new engineering challenges, as all these mirrors must function as a single large unit and remain perfectly aligned with each other. The James Webb Space Telescope features a mirror composed of 18 segments, each of which required meticulous and lengthy alignment. But the extremely large telescope will have 798 such mirrors. This makes it the central component of the entire astronomical machine currently under construction in Chile. And this is not just a large modular mirror, it is an incredibly complex system, a colossal mechanism whose precise and stable operation is the core objective of the entire project. Each segment is 1.45 meters wide, 5 centimeters thick, and weighs 250 kilograms. When we say that each one must be precisely aligned, we mean an extraordinary level of accuracy. The deviation must be smaller than the wavelength of the light being collected. For visible light, this is between 380 and 700 nanometers, tens of thousands of times smaller than a millimeter. This means you cannot simply cast the mirrors and position them once with perfect alignment. Tiny shifts will occur constantly, during telescope movement, due to wind, and even from changes in ambient temperature. As a result, each segment requires an entire infrastructure dedicated to maintaining its stability and alignment relative to its neighbors. The allowable deviations are within mere tens of nanometers, and this precision must be maintained across nearly 800 segments. Each mirror will be equipped with 27 specialized actuators that can adjust its shape, compensating for optical aberrations caused by gravity and external factors. Additionally, each segment will be able to adjust its height and rotate relative to the entire structure, with a maximum movement range of 10 millimeters and an accuracy of up to 2 nanometers. Naturally, all of this will be controlled automatically rather than manually. The mirrors will be equipped with sensors that continuously measure the shift and gap relative to adjacent segments with the required precision. To ensure proper operation and timely maintenance of the primary mirror, its support structure will consist of 3 levels. The upper level is the frame that directly supports the 798 segments. This surface has openings providing access to the components of each segment. Beneath this level, there is an area with circular and radial corridors, allowing for segment removal and electronic maintenance. Overall, the segments will be grouped into 6 sectors, forming the massive primary mirror, known as M1. Each sector will consist of 133 mirrors, which will differ in shape and optical characteristics. In other words, there are 133 different types of segments, and together they form one of the 6 sectors. In reality, additional spare segments will be cast, enough to assemble an entire extra sector. This ensures that any segment can be replaced quickly without waiting for a new one to be manufactured. These replacements will occur regularly. The reason is that the astronomical requirements for the mirrors are so stringent that each segment must have its coating removed and reapplied every 18 months. However, given the number of segments, this procedure must be performed daily, on 2 segments at a time. As a result, mirror maintenance will be one of the most costly yet crucial aspects of the telescope's operation. The journey of these mirrors to the telescope begins in Germany. The raw blanks are produced by the company Schott from a glass ceramic material called Zerodur, which has an extremely low thermal expansion coefficient. Initially, they are cast into a round shape. Then, in France, another company, Safran Riosk, cuts the blanks into hexagons and performs the polishing. This is the same company that polished the mirror segments for the James Webb Space Telescope. The grinding and polishing process is carried out with nanometer precision, after which the segments are fitted with their support structures. Finally, the mirrors undergo a final stage of polishing using ion beam technology. A beam of positively charged ions glides over the mirror's surface, eliminating any imperfections on a near-molecular level. Once delivered to Chile, the enormous ELT Technical Center will apply a reflective coating to the mirrors, consisting of thin layers of chromium, silver, and silicon. After acquiring their necessary reflective properties, the segments are stored in special containers until installation, which is scheduled for 2027. And in 2028, these mirrors are expected to collect their first light. Of course, no reflector telescope relies solely on a single large mirror. We have already mentioned the ELT's secondary mirror, which will be mounted at the top of the telescope tube. Unsurprisingly, it will be the largest secondary mirror in the world, with a diameter of 4 meters. But in total, the light path will pass through at least 5 mirrors. The M3, M4, and M5 mirrors will be mounted on a central tower, which is roughly the size of a 3-story building. Naturally, this component is another remarkable engineering achievement, as it must be attached to the center of the primary mirror's support structure. It cannot be too heavy to prevent deformation of the mirror, yet it must be rigid enough to avoid even the slightest bending under its own weight when the telescope tilts. Furthermore, wind must be able to pass freely through the tower to prevent the formation of air pockets that could distort the image. The importance of this structure is further emphasized by the fact that it will house one of the most critical mirrors, without which there would be no point in constructing something this colossal. At the very top of the tower will sit the M4 mirror, which will operate in adaptive optics mode. This mirror is the key to achieving the sharpness and image quality that astronomers anticipate. To appreciate the importance of its precise operation, just look at the difference between images of the center of our galaxy taken with and without adaptive optics on the Keck telescopes in Hawaii. Instead of a single blurry patch, dozens of bright central stars are revealed. Well, since you've been asking me to explain adaptive optics in more detail for quite some time, let's finally do it. Because when else would we talk about it if not in a video about the ELT? First of all, the layers of gas that separate Earth's surface from space and sustain life also constantly alter the path of every photon. Light bends when it passes through different mediums, something you can easily observe by looking at a straw or a spoon in a glass of water, where it appears tilted at an angle. The beam of light actually changes direction slightly, and even more, it slows down. But that's a topic for another video. For now, what's important is that just as light propagates differently through air and water, it also behaves differently when passing through air of varying temperatures. When photons transition from warm air to cooler air, they slow down and their path shifts. This wouldn't be such a big problem if the air weren't in constant motion. Its differently heated regions continuously mix, creating turbulence. And that atmospheric turbulence is what prevents astronomers from capturing sharp images of the night sky. The first step in overcoming this problem is, of course, to measure the distortions of incoming light waves in real time. To do this, an adaptive optics system uses specialized wavefront sensors. Essentially, these sensors function as ultra-fast digital cameras, highly sophisticated cameras, that detect, measure, and analyze distortions in the light. However, because atmospheric changes happen constantly and often very rapidly, the camera must capture these variations in real time, essentially producing a new correction map thousands of times per second. Even from personal experience, you know that taking a quick photo on a smartphone isn't always easy. It works best in bright daylight when there's plenty of light, allowing for a short exposure time so the camera doesn't have to collect photons for too long. Similarly, the wavefront sensor's camera needs a bright light source above the atmosphere to measure turbulence effectively in a fraction of a second. Stars can serve this purpose, as some are bright enough, but they can't always be conveniently located in the part of the sky where your telescope is pointing. That's why clever astronomers came up with artificial guide stars by shooting powerful lasers into the sky. You see, Earth's atmosphere contains a sodium layer a few kilometers thick, located about 90 kilometers above the surface, far above the turbulent layers that cause distortions. This sodium layer, by the way, is a natural consequence of meteorites burning up in our atmosphere. When a laser with a precise wavelength strikes this sodium layer, it excites the sodium atoms. They absorb the bright orange light and then re-emit it, effectively creating an artificial star that appears exactly where and when needed. These laser guide stars form the second key component of adaptive optics. Now that the wavefront sensor can continuously track the distortions in the light waves, the next step is to correct optical aberrations, essentially fixing image defects. This is the job of the third and most technologically advanced component of the system, a deformable mirror. This mirror is an extremely thin reflective membrane, mounted over an array of actuators, mechanisms that push and pull on the membrane at specific points. Every time the wavefront sensor takes a measurement, it sends the data to the adaptive mirror system, which deforms to counteract the atmospheric distortions. Thousands of actuators move the mirror's surface by just a few microns, and these corrections are made every millisecond, each actuator adjusting independently. So you can imagine the incredible computational and mechanical challenge this presents. The system that controls the mirror must execute thousands of movements per second, all in sync with the computer and wavefront sensor that continuously send data for real-time corrections. I'm not sure if it even needs to be said, but the ELT's adaptive mirror will be the largest ever built. Modern deformable mirrors are just slightly over a meter in diameter, but this one will be a massive 2.4 meters. It will be made up of 6 petal-shaped segments and will be less than 2 millimeters thick. The mirror will be mounted on a rigid frame containing 5,000 holes for the actuators that will hold and deform its surface. Interestingly, the mirror, or rather the membrane, will actually float above its rigid support at a distance of just 90 microns. In other words, it won't be rigidly fixed, but will instead be suspended in a magnetic field. This eliminates mechanical friction, which would otherwise interfere with the speed and precision of the corrections. To maintain the membrane in this position, special actuators are used. These are essentially small magnetic motors that push or pull sections of the membrane to correct incoming wavefront distortions. The principle behind them is similar to how a speaker works, which is why they are sometimes called voice coils. Each actuator consists of a magnetic core with a permanent magnetic field and a coil block. When an electric current flows through the coil, it generates its own magnetic field, which interacts with the permanent magnet's field. This creates a force that either pulls or pushes the membrane, depending on the current's polarity. These adjustments happen 1,000 times per second with an accuracy of just a few dozen nanometers, compensating not only for atmospheric turbulence, but also for vibrations from the telescope's own structure. A total of 6 or even 8 lasers will help the ELT's sensors measure distortions. These lasers will be so bright that aviation safety protocols require the system to automatically shut them off whenever an aircraft approaches. No, the lasers won't burn a hole through a plane, but they could temporarily blind sensitive optical and navigation equipment. Once the adaptive mirror completes its astonishing work, the light continues its journey to the fifth and final mirror in the telescope's system, M5. This mirror is also part of the adaptive optics system. It is capable of rapidly adjusting its tilt, further compensating for wind-induced vibrations and structural oscillations. Ultimately, M5 directs the light toward platforms where scientific instruments and auxiliary equipment are mounted. It can rotate and redirect the beam as needed, allowing astronomers to quickly switch between instruments and maximize the telescope's efficiency. Now you might think that after all these complex adjustments, the ELT's scientific instruments finally receive perfectly corrected light and can simply start gathering data. But nope, it's still not that simple. In reality, atmospheric aberrations can be so complex that even a high-tech adaptive mirror isn't always enough for certain observational conditions and scientific objectives. The reason is that Earth's atmosphere isn't just a single thick layer of gas. It consists of multiple layers, each with different wind speeds and turbulence levels at different altitudes. For example, the boundary layer, the one closest to Earth's surface, usually has the strongest turbulence. Meanwhile, at an altitude of 10 to 20 kilometers, atmospheric dynamics behave quite differently. Because of this, the extremely large telescope can operate in different adaptive optics modes. One option is to correct only for ground-level turbulence, which is relatively uniform across the entire field of view. This allows the telescope to observe a larger portion of the sky, useful in certain cases. But image quality won't be optimal since upper atmospheric layers will still cause distortions. Alternatively, astronomers can measure turbulence across multiple layers and achieve extremely sharp images, but only within a limited region of the sky. There's also a third approach, correcting for each atmospheric layer separately. The ELT can actually do this using an additional optical instrument called Morpho. Morpho is essentially an extra adaptive optics module with 2 additional deformable mirrors, each capable of correcting distortions from specific atmospheric layers. The system uses laser guide stars and bright natural stars to create a kind of 3D map of atmospheric distortions and applies precise corrections accordingly. This allows the telescope to maintain both a moderate field of view and excellent image quality. Morpho won't operate independently. It will serve as a supporting system for scientific instruments, delivering exceptional spatial resolution. It will enable multiple adaptive optics modes depending on specific research needs. To keep the runtime from getting too long, we'll cover the scientific instruments in future episodes, closer to the telescope's commissioning. The main takeaway is that they will potentially receive light from cosmic objects at a level of quality never before seen in ground-based astronomy. So, what kind of science will this bring us? Well, this is one of those rare moments when I can gladly say, I don't know. We can talk at length about the possible discoveries the telescope might make, but that would be like pointing a finger at the sky. Don't get me wrong. Of course, there's an official list of scientific goals, which you can easily check out on the ELT's website. It includes everything from the solar system to galaxies, cosmology, and, of course, exoplanets. But the truth is, no one can predict exactly how all the technical advantages of the telescope will expand our knowledge of the universe. In the original construction plans for the Hubble Space Telescope, none of its now iconic discoveries were even mentioned as potential objectives. In the late 1980s, we had no idea about the water plumes on Europa or the accelerating expansion of the universe. Before the launch of Webb, few expected to see ancient galaxies appear so large and bright, and we still don't fully understand the scientific consequences of that discovery. In a way, stated scientific goals are more like a marketing pitch for space agencies and governments that fund these projects. That's not to say there's anything wrong with having scientific goals. But in reality, astronomers often think differently. They know that simply seeing further and sharper means they can achieve far more than the original mission objectives. Unexpected discoveries are often even more important than the ones outlined during a telescope's development. The bottom line? A 39-meter mirror and cutting-edge adaptive optics set the stage for a major astronomical breakthrough. Compared to Hubble, which also observes the universe primarily in visible light, the ELT will have 16 times the resolution. That means astronomers will be able to see 16 times more detail. On the other hand, comparing it to Webb wouldn't be entirely fair, as these telescopes serve different purposes. Yes, ELT will collect far more light. Its mirror is 6 times wider in diameter. But Webb has its own strengths. By studying the universe in the mid-infrared, Webb excels at detecting cold objects, forming stars and planets, as well as the most distant galaxies from the cosmic dawn. ELT, or any ground-based telescope for that matter, will likely never surpass the premier space observatory in that field. However, when it comes to exoplanets, galaxies, and objects within the Milky Way, ELT could truly take research to the next level. So, instead of comparing them, we should see them as complementary. And as for the question of what the next giant optical telescope will discover, don't believe anyone who claims they know, because no one does. And that's actually amazing. It's far more exciting not just to talk about things we expect to see, but also about the things we haven't even imagined yet.